Guys, welcome back to the tutorials on basics of quantum computation. And so let's start with some recap. Yeah, so last day completed the postulates of quantum mechanics. So let's review them once. So the first postulate was the system postulate. And it said that for every quantum mechanical system, you will have some complex Hilbert space which is associated with it. And we learned what a Hilbert space is. The Hilbert space is just a vector space with inner product and with the additional condition of Cauchy complete. And we saw that the condition of Cauchy completeness meant that there are no holes or gaps in the space. And complex Hilbert space meant that the Hilbert space was defined on the field of complex numbers on the field of C. And if, for example, the system is some electron spin or polarization of photon or some two-level quantum system, or in general in a qubit system, then the Hilbert space which is associated with that system will be C2. Sorry. Uh, huh. And since we would be dealing with qubits for the majority of our tutorials, so we would be dealing with the Hilbert space of C2. And the second postulate was the state postulate. And it said that any pure state of the system is can be described by a vector in the Hilbert space Hs. So some vector psi, which is part of the Hilbert space Hs. And we assigned the meaning of total probability to the norm squared of the um, state vector. So we defined that the norm squared of psi is the total probability, and since the total probability will be 1, so this will be 1. So in other words, we defined that any state or any pure state of the system is basically a unit vector in the Hilbert space. And for the Hilbert space of our interest C2, any state vector ket psi can be written as a column vector C1, C2. Of course, C1, C2 here are complex numbers, and you can write this as C1, 0 and C2, 1, where 0 and 1 are these column vectors. And the third postulate was the measurement and collapse postulate. And it said that if there is any observable in the sense that anything that you can measure, then in quantum mechanics, you will have a Hermitian operator associated with it. So say the Hermitian operator is O hat here. So it says that if you do a measurement, is it being recorded? It is being streamed on YouTube, I think. Yeah, it is being recorded in that way. Okay. Uh, okay. Now, it says that on performing a measurement, one of the eigenvalues of this operator O will be obtained on doing the measurement. And suppose you have got a certain eigenvalue, and then after the measurement, the state will collapse to the corresponding eigenvector. Now, with what probability will we get a certain eigenvalue? That was given by Born rule. And it says that if the eigenvalues of O are, say, lambda 1, lambda 2, up to lambda n, with the corresponding eigenvectors f1, f2, up to fn, then, and if the system is in state psi, then the probability of getting a certain eigenvalue, say lambda I, on measuring O hat, is nothing but the projection of psi along fi and mod squared of that. So the projection of psi along fi is just inner product of fi and psi. And if you take the mod squared of that, you just get the probability. And the last postulate in the that we discussed last day is the unitary evolution postulate. And it says that the evolution of a closed quantum system is described by a unitary transformation. So, say for example, if you have state psi at T1, then if you apply a unitary which takes the state from the time T1 to T2, then this will be a unitary operator acting on psi T1 that will give you the a state at time T2. Now, how would you obtain this? How can we know that how will U T1 T2 look like? You can get that from the Schrodinger's equation, which is a differential equator psi. Okay, and last day we ended with a question that given that the dynamics is dynamics of a quantum system, of a closed quantum system, is given by the Schrodinger's equation, given this information. So Schrodinger's equation is this equation. To justify, given this information, so Schrodinger's equation is this equation, taking a complex so hold on for a second. We have some technical difficulty. Just bear with. Okay. Sorry for the inconvenience. Okay, so there was a uh, question. I think there's a few questions in the chat. Let me see. Yeah, so one was what is the meaning of a closed quantum system here? So a closed quantum system is a system which is not interacting with the environment. Okay. So for example, if you're taking the spin of an electron here, so if I'm saying that, okay, this electron is a closed quantum system, that means it is not interacting with its environment. Is that okay? Uh, okay. And acha, what is the where noise is not included? Oh, not necessarily that its noise is not included in the system. Um, Yeah, so if a system is an open quantum system, noise can arise, but it's not necessary. Okay. And why is such a condition necessary for the system? Okay, so basically, it's not necessary for the system. You can have open quantum systems, but as we shall see later, you can consider open quantum systems to be special cases of closed quantum system. As in, you can take the system and the environment to be a closed system. Then you look at how the system and environment is together evolving, and then you can just ignore how the environment is evolving, and you can only look at how the system is evolving. So that is something we will come to later on. So for the time being, what the postulate tells us is what will happen for unitary evolution, that is for a closed system. Okay, right. And so any idea on this question that I had asked in the last class? So basically, what I was trying to ask is, what if my Hilbert space is real, for example? Okay. So let me try to give you the answer to this. So if my Hilbert space is real, so then let's say my Hilbert space is R2 instead of C2. Okay, that is a real Hilbert space. The field is not complex numbers but real numbers. So if I have a state like this, then what is the left hand side of my Schrodinger equation? So this part. Okay, so it says IH cross d psi dt. So if psi is real and we have a I here, so this is imaginary. And on the right hand side, we have H psi. Now we know that since we have taken a real vector, psi is real. So this psi is also real. So in order for LHS to be equal to RHS, if LHS is imaginary, RHS has to be imaginary. And if psi is real, then only imaginary thing where it can arise is the Hamiltonian. So this has to be imaginary or complex in general.
Sir, you are not audible.
Okay, again, for some reason, the internet is not working properly today. So again, sorry for the inconvenience. Just hold on for 2 minutes, okay?
Yeah. Huh. So let's go over what we were doing once again. So we had assumed that so we were trying to answer the question that what will happen if my Hilbert space is real? Okay. So now we have taken some vector psi, which I have assumed is a member of the vector space R2, which is a real vector space and not a complex vector space. And we were trying to find out that in such a case, what are the real and imaginary? So there's a I here, root over of -1. So the left hand side is imaginary. And from there, we concluded that if psi is real here and this is imaginary, then H, this operator, has to be complex. Okay. So H has to be complex. This was our conclusion. But H is acting on a Hilbert space. Now it is acting on which Hilbert space? It is acting on R2. So if H is an operator that is acting on R2, then H has to be real, right? So now here we have a contradiction, because in order to make left hand side and right hand side of the Schrodinger equation equal, like even in principle, if they have to be equal, then we can see that uh, we cannot have a real vector space. If we have a real vector space, then this operator will try to be complex, but any operator on a real vector space has to be real. Okay, so here we have a contradiction. And so if I assume that Schrodinger equation is correct, then I cannot have a complex real vector space. I have to have a complex vector space. Is it okay with all of you? Okay, so now, so if there are any questions till this part on whatever we have done in last class, Schrodinger equation is the base. No, Schrodinger equation is not the base. See, we have the four postulates of quantum mechanics now that I talked about. So Schrodinger equation is a part of the fourth postulate, which is the unitary evolution postulate. Okay, so Schrodinger equation is not the base, but what I was trying to show is that they are. Oh, unitary operator, yes, from the Schrodinger equation. Okay, let me first answer Karthik's question. Okay, with Schrodinger equation is the base. No, the four postulates that we have, that I have told you, these are like it's a simplified version of the postulates, but in any case, these are the base. Okay, they together form the base. What I was trying to show you is that the postulates are self-consistent, as in introducing the Schrodinger equation does not mess with my first postulate, which is the complex vector space postulate. Okay, so this system postulate. Is that okay? And so Ajay asked how to find unitary operator. So unitary operator you can find from the Schrodinger equation. Last time I told you, if you remember, that if h is say time independent, then you can find the unitary very easily. It will just be e to the power minus something like this. Okay. Is that clear to you guys? Okay. 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 So any other questions till this part, based on what we have done, say till the last class? Any problems? Okay. So, if not, then let us go back to our old problem of Stern-Gerlach experiment. Okay. So let's review the problem once. So what did we have? We had an oven here, which was generating a beam of silver atoms, and then we had a screen, and then inside the apparatus we had a non-uniform magnetic field, which was uh, generated by pole pieces like that. Okay, and we saw that according to classical mechanics, what we expected is that okay, the electrons will come here, and then the electrons would be all over the screen. Okay, they will be detected all over the screen. But in the experiment, we observed that there were only two spots which were visible. So the electrons either hit here and hit here. And if this apparatus is oriented along some n roof, then we concluded that okay, the spin from here, that the spin angular momentum is corresponding to this, we found is plus h cross by 2 and minus h cross by 2. Okay, so this is what we found in the Stern-Gerlach apparatus. So now let us try to look at its formulation from now that we know but at that time we didn't know the postulates of quantum mechanics or how quantum mechanics works. But now that we equipped with that knowledge, let's try to explain this Stern-Gerlach experiment again. Okay. So now this whole apparatus, as we generally do, we just encapsulate the whole thing inside a box. Just consider it as a black box. And Stern-Gerlach apparatus oriented along the n roof direction, for example, uh, that what it does is if you give so from the oven atoms are coming or we can actually consider electrons, because as we had seen that only the unpaired electron in the atom was playing a role, so we can just say that okay, a beam of electrons are coming, and then inside the Stern-Gerlach it gets divided like this, and at the output we put a screen and we get some spots. Okay, now the measurement happens only when we put the screen. This is very important. So if we do not put the screen, then we wouldn't have understood where are the electrons going. So putting the screen is basically like putting the Stern-Gerlach apparatus and then finally putting the screen amounts to measuring the nth component of the angular moment. But according to the postulates, we know, so the nth component of angular momentum is an observable. So according to quantum mechanics, we know that any observable can be represented by a corresponding Hermitian operator. So this is actually measuring Sn hat. So this Hermitian operator Sn hat. Okay. And when we measure, we are getting either Sn minus h cross by 2 is then plus h cross by 2. And now let us look at how this Sn looks like. Okay. So this is something like h cross by 2 cos theta, sin theta e to the power minus I phi sine theta e to the power I phi and cos theta. So what is this theta and phi? So theta and phi corresponds to the direction, this n roof direction. So let's say we have this x, y, z coordinates in the real space. So I define a certain direction n hat, and here this angle, the angle it makes with the z axis, we call it theta. And if we take a projection on the xy plane, the angle it is making with the x axis is phi. Okay. Now, of course, if this is the case, then n hat will be, so the x component will be sine theta cos phi, and y component will be sine theta sine phi and cos theta. Now, you might be thinking, okay, how did I dream up this operator? So you can actually derive it, but the derivation is beyond the course of beyond the scope of this tutorial sessions. So if you want to actually know how this is derived, then you can look at the book Quantum Mechanics by Bransden and Joachim. You can look at the chapter of angular momentum. But for the time being, let's assume that we already know this. We know that Sn comes in this form. Now, as I had shown you yesterday, how to calculate the eigenvalues and eigenvectors. So I won't show you this calculation again, but you can check that eigenvalues are Sn plus h cross by 2 and Sn minus h cross by 2. Okay, so see, this matches with our experimental results also now. So previously by classical mechanics, we didn't, the theory of classical mechanics did not tell me that only two values are possible. But here quantum mechanics actually explicitly tells me that only these two values of Sn are possible. Okay. So that's one thing that it explains. And now, corresponding to this, say Sn plus h cross by 2, if you find the eigenvector, then so for Sn, let's say Sn plus h cross by 2. So this again you can calculate and check. I had shown you how to do the calculation yesterday. So you can find that this is something like cos theta by 2 e to the power I phi sine theta by 2. This is the up n corresponding to Sn plus h cross by 2, or you can write it as uh, cos theta by 2 0 plus e to the power I phi sine theta by 2 1. And similarly for Sn minus h cross by 2, we get the following eigenvector. This is sine theta by 2 e to the power I phi cos theta by 2. So in a similar way, you can write this. So I'm not showing. You can figure it out on your own. Okay. Now, again, you can check that up n and down n are perpendicular. Okay, as in orthogonal. I'm sorry, orthogonal. So, and they are also normalized. Till now, is this okay? Because the rest of the lecture will depend on these few equations. If there is any problem, you can let me know. Okay, so now moving on. So um, now let me ask you the following question. So here in this example, we had placed the screen somewhere. Okay. Now we had placed the screen in the entire portion. Now let's say I remove the screen from here and I only place the screen here. Okay. Then is it still a measurement? Like if I just put the screen only in front of this so that this goes through. Okay. Can you explain how this is a measurement?
So we can take the inner product with this particular component of Sn, like corresponding to minus h cross by 2 of the particular state.
Right. Yeah, that you can take. You can take the internal product and you can take out the probabilities. But what I'm asking is that suppose if I have put the screen here, then I am measuring only the spins with like spin down ones, na? The Sn minus h cross by 2 ones. So am I still measuring Sn plus h cross by 2? Because I am letting the Sn plus h cross by 2 pass. I am not putting a screen there. Any
Still,
ideas?
it's sir, it's still a
Mm-hmm.
measurement. If we are still
Mm-hmm.
measuring the like spin down component, so
Yeah.
it just we are not measuring the spin up component, but it is still a measurement, right?
Right. So yeah, I think I know where you're getting at. I think you have understood it properly. But still, let me, for the rest of you, let me reiterate what you have said. So basically, let's now take a single electron instead of many electrons. Okay. If you take a single electron, then it will go here with some probability, here with some probability. Now, let's say I know that in some time duration, say in the time interval T1 to T2, I know what this time interval is. I know that the electron would come at the out. Okay. Or rather, it would reach the screen. Okay. So in the during this interval T1, T2. So what would I do? I would try to see within this interval whether that single electron is coming here and hitting or not. So if it hits, for example, so if it comes here and hits, then I know that it is Sn minus h cross by 2. And after this happens, the electron has collapsed to the state up n, right? But suppose the same situation, let's take, okay? So suppose it does not come here in the interval T1 to T2, but we know that it should reach the screen within this interval. Okay, then I will conclude that okay, since it has not come here, it has gone there, right? So the absence of the electron here is now the measurement. Since this approach works because there are only two outputs. Okay, if there were more outputs, then this would not have worked. So if I If it is not coming in, then it has come there. So after the electron has passed this screen, then it actually collapses to, so we know that Sn is plus h cross by 2, and it has collapsed to the state up n. Is that okay? Okay. Now, uh, suppose this was with single electrons. Now, if I say take multiple electrons, for example, let's say I have got 100 electrons here. Then let's assume that, so if it is coming from the oven, then they're all randomly oriented, right? Then we know that half of them will go above, half of them will go below. So say 50, I detect 50 electrons here out of the 100. So I already know that the rest 50 must have passed through, and they must have collapsed to the up n state, right? Sorry, this is down n, this is up n. So given this, would you agree now? Okay, even if I place the screen on one path, it is still a measurement. And if you have any confusion regarding this, let me know. Okay. So I'm assuming that you guys have understood, and so let me move on. So if you remember, then we had considered some special cases when we were looking at the Stern-Gerlach experiment, and one of them, a few of them did not match with our classical intuition. So let's first of consider the case which did match with our intuition. So in the case one, if you remember, we took a Stern-Gerlach along Z. So we had some randomly oriented electrons from the oven, and we placed a screen here. We let it pass, and then we fed it to another Stern-Gerlach apparatus, which is oriented along the same direction, and we put another screen here. So let's say this is screen 1, this is screen 2. So the question now is, okay, what will we see on screen 2? Let us try to answer this question from our knowledge of quantum mechanics now. So since this is SGZ, then the measurement which we are doing here is actually a measurement of SZ hat. So SZ hat, now we know what SN hat looks like, right? So we had written it here, SN hat. So if I want to find SZ hat, what will I do? I'll just put the corresponding theta and phi. So you can find that for theta 0 and phi 0, you get SZ hat. So if you put theta 0, this will be 1. Sorry, this is minus cos theta actually. 1 minus 1, and this would be 0. So SZ hat would be something like h cross by 2, 1, 0, 0, minus 1. Okay. Since theta 0 and phi 0 for the z direction. And as we have seen, for whatever, which one do you want to repeat? Which part should I repeat? Oh, okay. Great, great. Okay. So now as we have seen, ki whatever direction the Stern Gerlach is oriented in, so the eigen values are going to be plus h cross by 2 and minus h cross by 2, regardless of the direction. So that we know. Now, if you calculate the eigenvectors, then you can just put again theta equal to 0, phi equal to 0 in those relations, and you will find that this comes out to be just 1, 0, which is just get 0. And corresponding to minus h cross by 2, you will have the down z, which is 0, 1, or just get 1. Okay, so um, what we are doing is that we are putting a screen in the lower part. So suppose if you have say an ensemble of electrons coming from here, so all the ones which are in z equal to minus h cross by 2, they are getting measured here, and consequently in the upper half everything is that is there we know is in plus h cross by 2 state, or we can say that it has collapsed to the up z state. Okay, now what are we measuring here in screen 2? Again we are measuring the sz hat, we are measuring. So from the laws of quantum mechanics, how can we predict ki how much of the electrons which are reaching the second Stern-Gerlach apparatus? Let's say this is the second one, this is the first one. How many of these electrons will be in will hit the upper part of the screen and hit the lower part of the screen? No, it's not 25% actually, but I am not asking for you the exact answer if it is 100 or 0 or 25 or 50, but rather, so like say if there are 100 here, so you are saying that it will 25% will hit. No, that's not correct. So, but I'm asking ki how can you find out ki how many will hit in the upper hand and how many will hit in the lower hand of the Stern-Gerlach apparatus? Using probabilities, that is true. Here we can use alternate basis. Uh, Not really. You don't really need to use any other basis. Yeah, it is okay if you work in this basis only. So yeah, using probabilities. So how do you calculate the probabilities? Using Born rule, right? So let's do that. So let's consider that now this is the state, right? Let's call it psi 1. So I want to find the probability that it hits in the upper half, for example. So if it is hitting in the upper half, then I can measure that it is set plus h cross by 2, right? Now, what is the uh, eigenvector corresponding to sz plus h cross by 2? This is upz or 0. Okay. And my state is in psi 1. So what will I do? I'll just take a component of upset of psi along upset, psi 1 along upset, and mod square. But notice that here psi 1 is nothing but upz itself. So basically we are trying to find the component of upz along upz. Now, as I said, mentioned earlier, because of the because we have defined the total probability as the norm squared, all the vectors are unit vectors. So the component of any vector along itself will be one only. Okay. And if you try to find out the probability of getting sz minus h cross by 2, then you will get this. And up z and down z we had already previously seen they are orthogonal, so this is 0. Only after measurement? No, 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 no. The component of any vector along itself is 1 always. Okay. Because the vector is a unit vector, na? So the length. So okay, now let's go back to our familiar example of R3. Okay, if you have a unit vector, say I, and you want to uh, um, measure the component along itself, it will always be one, no? So in quantum mechanics, all the state vectors are unit vectors, so that will be always one. Okay. Okay, so you can see that probability of finding sz h cross by 2 is 1 and probability of finding sz minus h cross by 2 is 0. And that means everything which comes here will go through and hit here. So we will measure here only sz plus h cross over 2, and of course it was already in the upz state, so technically it does not since it was already in upz, so it doesn't have to collapse again. So it's yeah. So is this part clear ki why this is happening? And this is something we expected from classical mechanics also. Okay, if you have something in the upz state, if you measure again its z component, you will again get upz only. You won't get anything in dowz. So you don't get anything because probability of finding sz minus h cross by 2 is 0. So is this point clear? Okay. Now let's then go on to the second case that we had discussed at that time in our first class. So let's go to case number 2. Now here you have something coming out of the oven. So you have put a Stern-Gerlach along Z again. You have put this screen, and then instead of passing it through another Stern-Gerlach along Z as we did before, let's pass it through a Stern-Gerlach along X. Okay, and then again let's put a screen here and let's number the screen 1 and 2. The question again is, okay, what will we see on screen 2? So any ideas? Uh, you will get 0. Okay, let's see. Let's see. Okay. So whatever is coming here, you expect that this is in the up Z state, right? Because I have blocked all the down Z state, so this is only up Z. Now let's say again this is psi1, and uh, here we are measuring when we are placing the Stern-Gerlach along X, and we are measuring here, then yeah, like yeah, you're right. Classically, you would expect 0. If it is in upset state, you would expect that it is 0. But let's see what it is quantum mechanics. So you're actually measuring Sx here. Okay. So let's again look at how this would look like. So again, in that equation, if you just put x will correspond to theta equal to pi by 2 and pi equal to 0. Okay. And if you put those values, you will get this h cross by 2, 0, 1, 1, 0, this matrix. And as usual, Sx values, possible values will be h cross by 2 and minus h cross by 2. Now, let's find the probability of getting in the upper hand of the Stern-Gerlach experiment. So basically of measuring Sx equal to plus h cross by 2. Okay. Acha, I should have mentioned the eigenvectors also before I do this. Uh, okay, so the eigenvector corresponding to Sx plus h cross by 2 is apex, which we also sometimes write as plus ket, and that is 0 plus 1 by rho. And this is down x, and this we also write as ket minus, and this is 0 minus 1 by root. The reason we use ket plus is because this is 0 plus 1 and ket minus because this is 0 minus 1. All right. Now, if I want to find the probability that Sx is equal to plus h cross by 2, what will I have to do again? I have to find the component of psi, my state, along the eigenvector corresponding to Sx plus h cross by 2, which is apex. So what I would do is just apex psi inner product whole square. Okay. Now, apex is so the ket apex I have given here is ket 0 plus ket 1 by root 2. So bra apex will just be bra 0 plus bra 1 by root 2. So it would be something like this. And my state was in upset. Okay, upset is just ket 0. Okay. পনেরো Okay, so this is what calculate this, then basically you have the inner product bra 0 plus bra with ket 0. So this would be just inner product of 0, inner product of 1 0 by root 2 whole squared. Now this is 1 because again the component of the vector along itself, and this is oh, my voice is breaking. Is it okay now?
It's fine.
Is it better? It's fine. Uh, okay, okay. So let's see. Hopefully it would be okay from now. All right. So if you take the kit 1 0, since these are orthogonal, then this inner product will give you 0. And that means this is 1 by root 2 whole squared and is half. All right. And you can also find in a similar way probability of say Sx minus h cross by 2 as the component of psi 1 along um, this down x squared, or so basically it measures the projection of up z along down x. Okay, and yeah, we could go ahead and calculate this, but we know that the total probability is 1, so we know that this will be half. So although classically we would expect that nothing would come out of here because the spin is in the up z state, what we find from quantum mechanics is that there is half probability that the electron will hit here, and there's a half probability that the electron will hit here. So yeah, and so 50%, so 50% comes here and 50% comes here. Okay, so right now let's consider case 3. So is this one clear to everybody? Is there any question? Also, I should mention that when it hits here, we again know that it is in XX plus h cross by 2, and after it hits the screen, it collapses to apex and Sx minus h cross by 2. Yes, this is because of superposition, because you see that what is 0 and 1? 0 and 1 are nothing but up z and down z. So apex is nothing but a superposition of up z and down z. Or the other way around, you can also find out up x is a superposition of say up z and down z. Okay. and similarly for down x. Is that okay, Karthik? Hmm. Right. So yeah, superposition is at play here, and we will like look at what it means to be a quantum superposition in more details later on, like in more fundamental terms later on, when we will contrast it with a classical mixture. So we will look at what is the difference between a classical mixture and a quantum superposition, but not today, later on. Okay, so hopefully this is clear ki how this is happening. Okay. So now let's move on to case 3. Let's copy this. Okay. And paste. All right. Now, here, let's do some modifications to this. So, uh, like in the previous case, we passed the upz component to Stern like oriented along x. Now we put a screen here so that the measurement takes place. And after this measurement happens, we know that whatever is coming out of here is in the apex state. And now we put another Stern Gerlach along Z. And finally, we put a big screen. And so there are now three screens. Now we want to know, okay, what will appear on screen 3. Hmm, huh, so now my state is in site 2, and when I'm passing it through a Stern Gerlach and putting a screen, I'm basically measuring a set. Okay, so now any guesses as to what you will see? Okay, sorry. Hmm. Okay. Sorry, the screen got unshared for a moment. Okay, so any ideas? Neon. Only upstate. Uh, See, think of it like this. When you had just upstate state, you got both apex and up down. Now, when you have just apex state, will you just get upz? Because see, the possibilities of getting here are upz and downz. So if it was along x, then you would be right. Ki only apex will go through. Like you will only see apex here. But here, this is in apex state and this is oriented along Z. Right, you would get both up and down. Okay. And let's again, so the calculation would be very similar again. So, but let's still go through that. So if I want to find the probability that I get Z plus H cross by 2, what will I do? Just take this component and upset is just 0, and this would be 0 plus 1 by root 2 mod squared, and you can find that this is half. And similarly, you can see that probability of Z minus h cross by 2 will be half. So yes, you will find both um, um, when you measure both upset and downside. But you are right. Aja has said ki only upstate. You are right from a classical point of view, because in classical point of view, you see the first Stern-Gerlach filters out the upset state. The second Stern-Gerlach filters out the apex state. So it is expected that since here we have got only particles with Sz equal to plus h cross by 2, from classical mechanics, you will expect that there will be only Sz plus h cross by 2. But from quantum mechanics, we see that that is not the case. We get both plus h cross by 2 and minus h cross by 2, and which explains my experiment. Is it okay? Okay. And today we will conclude our session early because this weather is not very good and we are having internet connectivity issues. So maybe we will continue with the rest of the discussion. So we will learn a little bit about global phases and then um, global phases and block vectors and block sphere. We'll learn about them in the next class. Okay, so we will end it here. In the meantime, if you guys have any questions, uh, can I share my email? I guess, yeah, I think I can. Yeah, okay, I'll share it. Okay. Okay, I have shared my email here. So if you have any queries, you can also reach me by emails. No problem. Uh, so if you guys have any questions about this, please let me know. Okay, let me wait for 2 more minutes. If uh, nothing else, then I'll end the meeting.